Okay, astrophysics today. It's going to be very different. I don't know if I'm going to do any calculations at all, actually, because I just work with assignments. So some days I'm just going to work with assignments, but to use my time efficiently, what I'm going to do is in the evenings like this, I can explain the steps I went through. Maybe I see some issue, maybe, yeah, you explain it, you learn, of course. So I can explain through, I did a task and then the assignment, right? So I can explain steps through it. Okay. So exercise 1A2, this doesn't matter. Okay. So what we have is that we have data for rain. The first column shows that year. Next 12 columns, the yearly rainfall in millimeters that month, a month for the given year, and the final column shows the yearly rainfall. Before starting this exercise, yeah, it doesn't matter. Okay? So we are now supposed to create a histogram without using np.histogram. So we are meant to do this from scratch. Okay, so choose one month and make an array with the rainfall for this month year by year, okay? So let's go to the code here. Of course, 1A and 1A2. So what I did in order to more modularize, you could say, I just because I've been a programmer before and my brain just works a lot better this when I code this style. So I just put each piece in a function. It just makes everything so much simpler. Okay. So I had this month data, right? So what I did is I opened this file. Like we said, it was this file right here, right? On the file, we can go to it. You see it here, actually. Yeah. This is just a preview, but you see it here. It was like I said. I just read the lines and skipped the first two, but the first two doesn't, of course, add to anything. So where was, no, not the checklist. There you go. The first two you see just comments. Skip those two. Then what I did, I created an array where the shape is just the length, so the amount of lines, because there are years, right? And for each year, you will have a column of the month for that year, right? So that's how I did it, just to make things a little bit simpler, right? Then I just went through the data. So this is just some empty array with zeros. Then I went through the data, of course, normal stuff, you strip, so remove any white space, and then you split, of course. And then I go through just for j in range 12, right? Because 12 months, of course. And then I just set I comma j and then j plus 1 here, as you see, right? That should be very, very neat. I just have to see. Why did I do so months I comma j? Yeah, and of course the first data point was year, so that's why I have j plus 1 here, right? But I have the index from 0 to 11 in terms of the array, right? Close that file. I don't know, I think you don't need it, but I just did it anyway. Return the months, right? So here I get all the months, so I get rain data for all the months, right? Okay. Then we have bins data, because we're supposed to create bins. That's in the next one. So define 20 equally spaced bins between the smallest and largest value in your list. For instance, if your values range from yes, etc., etc. Okay, so here's I have just this empty array, bins data for all months. Then I just went through for every month. The reason being is that we're supposed, but further down, you do this for every month, actually. So it was a little bit silly for me, but you can view this just as a single month for M here, right? Okay, so if you just calculated the bins data for 1 month, you can go to that function. Then I use the smallest and the biggest. Then we had 20 bins, right? And then, of course, in order to have 20 bins, it's like that fence idea. You have to add one more. So I have smallest and then biggest, and of course, spacing between there. Then the bins data, I set lowest, highest. I set this as a dictionary because then I can, in the other functions, I could just pass around this dictionary. I like that because then I always have those values. I don't need to loop through a bunch of stuff and send. Suddenly this function takes in these values and then suddenly some other. Now I can just send in the same dictionary. So we have some kind of data dictionary. That's the idea here. Okay. Yes, now I just go through each of these bin. I set the lowest, the highest, midpoint, the string. This is just some nicety I wanted in case I need it. And then I append the lowest and highest, just these lists. And the midpoints, I'm going to explain why. The reason being is that we have to count how many times we see that bin. That's why I do that. Okay, so I need the lowest and the highest, right? And the midpoint. And then I just say counts is just this array. Not this list of 0 n elements. Yeah, just the bins. Okay, and then I just say for I in range length of the month, right? So I have for January, right? So I'm just January. So that's every year in January I go through. Then I go through each bin for that year. So for J in range N, right? And then I check if what I'm saying, if the lowest for my bin and highest for my bin is this year with that month, is that rain inside this bin? If it's so, I just count. And since I do it like 0 and equal, I miss on the last step because I have 0, so I have the lowest, so equal and bigger than the lowest, then I have smaller than the highest. When you do that, you will miss the last step. That's why I have this or month equal to the absolute biggest. Because if, let's say, our final value was 400, and if it was one value of 400, my bin will miss that. It will stop at 399 because less than, right? That's the idea. Okay. Then we just do normal mean and standard deviation. The reason being is that we want to do compare. So the next task here, we're going to create a probability distribution. That's why we are counting, just normal probability, nothing special. And the idea is so that we do actually the mean calculation, and we do the standard deviation calculation, and then we now use the bins instead to check, right? So I just use the bins, I count the occurrence of that bins, right? And I divide that over the total, and of course then I get the probability, and I compare that to just having the analytical solution. That is what I'm doing here. So that's why I'm saving. And the midpoints I'm saving, the reason being is that I use the midpoints for stating the bin, right? And also I use the midpoints also when I set up the graph. That's also the idea. So now we have everything for this bins data, and now I return that bins data, right? So we have that there. Okay, that's pretty cool. We can also plot, so that's what the last function here does. So we can plot the bins data and the Gaussian. The thing here is that actually if you can't see, I did some mistake here with the plot, but it's all right. The idea is correct, but the bar, this guy, this is entirely correct. So let's see, if we plot the bins data and the Gaussian just for, let's say, January. So you can see now, if I do that, it's just, no, not assignment. If you go to 1A, we're not going to take this task too seriously. It's the assignment that matters. Do I call it start? No, that makes no sense. It's 1A2.py. Yeah, and here you see. And obviously this is not Gaussian, of course, as you see here. So that is just the these are just those spins, and of course they're not too many, right, in terms of the counting data. But what we are actually doing further down the line is that we are collecting the mean value. If you collect the mean value for all years, so if you have the mean rainfall for that year and we collect all of those, we actually get the central limit theorem, and that is the last part of the last task. But we're going to move further on this. It's all right. We can actually try and plot that. You can see now if I plot the midpoints and the function with the midpoints, and now if I use the mean value, let's see if that is what I have. I just have to see. Yeah, and you see this is just much more normal, right? But it should be at 0. Yeah, it's some mistake, but that's not important. It's the assignment. But the general idea here is correct, especially the bins one. The other here I messed up, and my brain is very much hurting. Okay, let's move to the assignment, the important part here. And I followed the same principle. Now I added, of course, some... oh, you moron. I added some more comments here. That's just it. But otherwise, I follow the same approach by modularizing. It's just so much easier. So let's move to the assignment that we have. Okay, let's see. It's here, isn't it? There you go. 1A, yeah. So exercise 1A6. You need to have read all of part 1A in order to be able to solve this exercise. In this and the following exercise, you will need to access your solar system through the solar system class. And this is this pip package that they have. The only information you need here is the mass and the radius of your home planet. Your home planet is the planet with index 0. So we have a seed value, which is just a random value, or it's the seed for generating our random value. And it will generate, it's of course a pseudo-random, and it's a random planet or a solar system for our case. And we are going to choose just the first planet, so with index 0. Please check the documentation on the semester page on how to install tools, etc., and to obtain the numbers that you need. Note further that there are skeleton codes available. Yeah, I don't care about that. Yes. Included in one of the code skeleton. Yeah, I don't want this either. Yeah, okay. When you see the moment the particle seems correct, you can, yeah. Create a rocket. Okay, there we go. In this exercise, you will create a rocket engine to make a satellite escape the gravitational potential of your home planet. Your task is to create a simplified rocket engine which can accelerate a satellite with a weight of 100 of just a ton, of course. I visual mark what's nice. Plus the weight of fuel, which we will ignore for the moment, to escape velocity. Okay, so we need to get our rocket to escape velocity. Assume the size of your box is this here. So we have some box, we're going to simulate with particles. Of course, this is going to be our fuel tank, but I guess since it was so small, we're going to use many boxes, because using a huge fuel tank with particles that are like millions particles per width of a hair, that needs a pretty interesting computer, right? And I have a good computer, but not that good, right? So we are just going to instead divide fuel tank into small boxes. I guess this is the size for a small box. I'm not finished this task yet, but I guess that is it, and we're just going to multiply, right? Because it will be the same. Okay, the temperature of the gas is, what is it, 10 to the 1, 2, 3, 5? Is it 5? 1, 2, 3, no, it's 4. 1, 2, 3, yeah. 10 to the 4 Kelvin. And the number, or 30, like you could say, 10,000. And the number of particles in the box is 10 to the 5th. Assume all gas particles are hydrogen molecules, H2. We'll do this step by step. So first, calculate the escape velocity for your whole planet. We derived it last time, just conservation of energy. Of course, you have to set the mass of, we can write it. It's fun doing, so why not? So, of course, the potential energy, right? The total energy is, of course, kinetic and potential mechanical energy. You move gravitational on the one side, then, of course, it's positive. So what you end up with is then, of course, 1/2. It's good to do some physics. Which is just equal to G m, of course, over, that will just be, will it just be r squared then? Or will it just be r now, since we have, we don't have the direction there? Now I am a complete moron. Because usually you have r cubed and r. Yeah, it is of course an r squared formula. No, it's in terms of, oh, I was thinking about force. It's of course in terms of energy, that's r. Okay. Yeah, good to do some high school physics. So capital M here is the planet, and M is of course our satellite or rocket or whatever. Right, and just do simple algebra here. You get, of course, G. M goes away, so just have 2gm over r. And this is the escape velocity we need. So usually we have been given our planet in solar masses. No, in solar mass, so we have to multiply by the solar mass. And also you need to, I don't remember what units I went with. I have written it down. Okay, so here I also written the tasks here in steps. So I also follow everything from the bottom. So I start with, to get the system and the data dictionary, I have a function that is called initialize, right? Okay, we go to initialize. I have, this is my seed value. I initialize my system here. I also initialize random with, of course, 42. I set up the mass here and I multiply by the sun because I want it in kilo. The radius for my first planet can just stay in kilometers because that's pretty easy. I can work with that. Number of particles, the width of that box, I have that in meters. Temperature is in Kelvin. Period is that comes for later, and steps here, that also comes for later. So then I set, again, same idea, I set up a data dictionary, but now I just initialize with things I need. Mass, V-escape, which we haven't calculated, it's 0. Particles, box width. This is going to be temperature. What was sigma? Sigma is, yeah, we'll get back to that later. The initial position, remember this is particles, and when it comes to particles and gases, of course, statistics. So you have to, in order to create those particles, because what we want to do is simulate particles, use ideal gas law, increase, of course, increase temperature. And if you increase temperature and you, of course, increase density, then you, of course, increase pressure. You increase pressure, you increase momentum, which means that you throw particle one way and the rocket goes other way, right? Or you could say more specifically, thrust goes one way and rocket goes other way. That's what you do. So we need, of course, the initial position. That is just an array. So we had the number of particles, and the initial position is just the column. So we just have x, y, and z in each column. Same with the velocity, right? And then I just have an absolute value, because we need that too, initial as well, right? This I haven't decided yet what to do with, but we get to that later. Okay, so that's the initial setup. Then I have a function, get escape velocity. I take the data dictionary, I get mass and radius, and you see we just use the formula. There's a constant. Luckily for our case, in the packages there's also constants there, so you don't need to write in the constant for G or the constant for what you call it, constant for the mass of the helium, right? So you don't need to write that either, or the mass for the sun, for example, right? Okay, so that was the first task. Then in the second task, start the code by creating 2 arrays. one with the XYZ position of all n particles, and one with the VXY, velocity of n particles. Draw these random positions and velocity from their respective distributions as described. Yes. Okay, and position, remember, a particle doesn't favor a position in a box. He's just bumping around when I'm thinking about the initial position. Which means that it's equally likely for him to start at some point to the left, some point up, some point to the right. It doesn't matter which axis, right? And this is true, which means that's the uniform distribution. Okay, so I create also a function in order to generate this data here. So it's called generate position and velocity. Again, I just pass in the data dictionary. Again, now I can just get the values. I don't need to, oh, this needs n and this needs that. It's just so confusing. I like this. So I can just say n, it's in the data dictionary, the box width, and sigma. Yeah, sigma here is because velocities themselves, they follow a Gaussian distribution. It's from the Maxwell-Boltzmann distribution. It's actually just the components. The vector itself doesn't follow it. But the components do, right? Then, for a Gaussian distribution, mu is of course just 0. Nothing special about that. But we have to calculate a sigma, of course. And it has actually a very neat formula that for sigma. Have I calculated it? I think I have. I think I initialized it. Did I? See, now I have it as 0 there. Hit dictionary.sigma. Oh, I did it here, right? So you see the dictionary.sigma, just np.square root. Then we have the Boltzmann constant, and we have, of course, temperature, and we divide by the mass. That's how you get this is just from the example sheet. There's nothing that we have to calculate, but this is how you get sigma in this case. Okay. And here I set, of course, the data that I wanted. And I used that function that we were on, which was generate position and velocity for, again, the data dictionary. And go back here. I just write again. I write R0 here. Same shape, right? I fill these and then I put it back for a data dictionary. It just makes more sense to my brain. Then I have the absolute values. So what I do, I just go through all of the particles. So when I'm at a particle, I jump through every dimension for dimension in range 3. Then I can easily say that R, we use the uniform distribution like I said. With 0, it's between 0 and the box width. And that's of course, if the box is just a volume, it's the same, right, for z, y, and x. So I can just use that for all dimensions. And of course, I use the same thing here, but now it's a Gauss distribution. So I use mu and then sigma, of course, right? And that's, of course, also the same. A particle doesn't favor any dimension, right? Okay, now we have that. So what we do now? The thing we do now is that we also want, like I said, the absolute value. So now I just get the array, just a single array, so just represent a vector, like a 3-dimensional vector there. Same here. And then I just use linear algebra.norm, right, to normalize that array, because of course that is the absolute value. And then I set those two arrays there with that value, and I return everything here in the end. That should be very nice and neat. Okay, and now we can test our data. So having created the random particles positions and velocities, you can now use this to check A, if the mean kinetic energy of the particles in the gas is really 3/2 times kT, and B, that the mean absolute velocity of the gas particles really follows the expression you found in exercise 1A5. So first we test kinetic energy, then the velocity, right? So the expression is not that hard actually. So here is the idea I can show you. 1A, where are you? There you are. So 1A5, we want to solve for velocity analytically, right? And we just start with if I can take one more here. So what did I do there? No. Oh, there you go. Thank God. No, I didn't want that at all. What? I used some command I didn't want? No. This was annoying. Okay, get rid of this one. 1A. Okay, yeah. Yes, here you see for the component. And we want to get this one. What are you doing? Why did it cut off there? What's happening here? Yeah. Sometimes this just acts like, yeah, it doesn't care. Okay. Maybe I should restart. Is there a restart function here or something? No. This was stupid. Why did it do that? That's not cool at all. Yeah, let's try and restart it. This was annoying. Okay. Let's open SEEK backup. Then we can go back to part 1. Why is it 2.1a? Now everything is suddenly stupid. Okay, go back to 1a. I mean, if it cuts off this time, I'm going to be really mad. Okay, let's see. There we go. Yeah, so we're going to start with this expression, which is just equal to this. This is of course, our density function. It's everything here except v. And what we have is task is of course 1a there. So we have been given this. I've seen this of course before, and you use this guy. If you just manipulate it a little bit clever, you can use this guy and get the correct answer. Maybe we can do that for fun. You know, I like to do this painful stuff for fun, so let's just do some painful stuff for fun, right? The expression, goddamn, what was the expression again? I should have some mark command here. Okay, so the expression v is the integral from 0 to infinity. Then we have v, we have m over 2 pi k and t, just like that, and to the power of 3 over 2. Then what we have is e to the minus 1/2. Then we have mv squared divided by k and t, right? And then we have, in the end, just 4 pi, and then we have v squared. And of course dv, just like that. Okay, and we need that expression, that last integral there. Where is that expression? There you go. Okay, and we need that. That is what we need. So we need this 0 to infinity of just dx. And we have e to the minus x and x. That's equal to 1. Okay, so let's solve this. Okay, so I want to manipulate to that guy. There was another expression there, but this was the one that I used. So let's see how we can do it, right? You already see that you have e to the minus x, right? Which means that what you can do is call just the whole of this guy. Yeah, you can just call all of this is a perfect valid x, right? That's what you can do. And you could also change this for sigma as well. That's what I actually did, because it was annoying to have all of that stuff there. Because sigma, I think sigma squared, sigma squared is actually m over, was it m? No, it's kt, right? So it's just kt over m, right? So sigma is just k, t, and divided by m, just like that. Okay. Then we can, of course, rewrite our expression, because then, again, it just makes life a bit, not just a bit, but a lot simpler. And we have the same thing in that expression as well. Then we get, we have m, so m goes away. We have 2 pi, so 2 pi can just stay. So we have 1, and then we have 2 pi, and then if I divide by m, that means it goes down both sides by m, right? That's just sigma squared. That should make sense, and of course this should be 3/2. Then what we have is e to the minus, and then we have just 1/2. We just have v squared, and then it was minus just 2 sigma squared, just like that. And then of course what we have left here is 4 pi v and then dv. And now we are very much intact and can make our nice substitution. And wasn't it v squared? Yeah, it was v squared as well. And we have v there. Yes, perfect. So now we could state that x is equal to, you moron, x is equal to minus v squared. No, it was minus the first, so we can just use v squared and 2 sigma squared. And that means if I do dx with respect to dv, what do I get? I just get 2v. So 2 goes away, and what do I have? I just have v over, not 2, v over sigma squared. That means that, of course, dx is, or we can say dv instead, dv is, of course, just the opposite way. So just sigma squared over v, and then dx. Just like that. Okay, so let's see that we have done everything here properly. Let's see. Okay, and that last guy, I need to make a substitution for that last guy as well. Let's see that last guy. I need v squared, so we can set v squared over there. This nice thing here get rid of this v, right? That's what it does. What we end up is with sigma squared above that guy. You know what? I write this a little bit nonsensical, but yeah, that's what I do. So sigma squared, then we have 2 pi sigma squared 3/2. Oh yeah, why are you a moron? If it's squared, why do you need that? You just have sigma cubed, right? That means that we have 2 pi 3/2. Then we have sigma cubed, I mean, of course. Isn't that correct? That's the same as sigma cubed, right? Yes? But I had sigma squared there. Yeah, what are you? Are you a moron? What are you even talking about? I got this correct the last time. Let's see if I am a moron or not. Have I missed something here? I have sigma squared, that means I have sigma cubed, but then I get sigma. That's not correct. I need, let's see the formula. I need x. And then of course, I need sigma squared. Oh, I could substitute back. I can do that. Yeah, I can just leave 1 sigma outside. Ha, that works. So what we can do, we can just leave 1 sigma on the outside. You know what? I move it here. I can keep sigma squared there. we can move things that doesn't contribute here, right? I have 4 pi. That doesn't contribute either. So I have 4 pi. And like I said, I have sigma. Yeah, that should be all right. Then I can put v squared on top of that. V went out, and then I have e to the minus x, and then dx. That should be pretty good. Okay. Let's see. Now I need to manipulate. So I just have 2 there, right? Isn't that what we have? Yeah, we just have 2. So that's the only thing now I need to do. So my brain need to, yeah, work. Yeah, okay. 4 is the same as 2 squared. Let's see. Okay. So 2 squared over 2 over 3 over 2. I need to just 2 there. If I move 2 down, that's the same as 4. And then that 2 goes away. Shouldn't that just, yeah, be it? If I move in 2 squared. I feel like I make some mistake then. Won't I? Or not. I 2 squared. Oh, my brain today. It's hurting. So I 2 over 2, it's 4 over, that's of course 4 over 2. So that's just 2, square root of 2. No. Are you 4 over 2? Then I subtract by 3. That's just the square root of 2, but do I want the square root of 2? Yeah. I don't want the square root of 2. I just want 2 there. If I kept just 2 instead, I have 2 over 2 and minus. That's the square root, but I don't want. What am I even? 2 over 2. I could have 4. Why are my brain acting insane? Okay, that's it. Okay, so I could, of course, the bottom one is of course just square root of 2 times 2, you moron. Yeah, that's it. I could just move that one outside instead of making all this crazy nonsense. Yeah, that would have been better, right? So I can just move square root of 2 outside here. Then I would have a square root of 2. I also had pi, but I could just pi 3 over 2. And then I could, of course, have 2. Yes, that works. That works very well, right? Okay. I think that should be all right. Maybe I made some mistake, but the ideas here are good enough. 4 pi, I should have shortened that. That's 1 pi and 1/2. This is just 4 over the square root of 2 and this guy, right? And then, of course, the integral is 0. Now we have x, and now we have e minus x dx. And all of this should be 1, which means that we have 4 over at 2 pi. And I forget sigma as well. And that means that sigma, in this case, we need to now substitute sigma back. And sigma was just, that's the square root of kt and m. So everything here should be the square root, right? So we have 4, we have sigma, and that was just, in what direction was it? Kt, and then m, so we get 4, then I get square root, then I have a kt over 2 pi, and then m, just like that. And you can, of course, substitute in 4. And 4 squared is just it's, what is it? Square root of 2 cubed. No, that is no, of course, it's just square root of 2 to the 4th. Yeah, you moron. So you get in, of course, 2 to the 4th here. And then, of course, what you get is k, t, then 8, and then over pi. And that's correct. Yes. So even with being late and the brain being stupid, it works very well. Okay, so that's correct. I don't know why I was so slow on that fraction, but who cares? But that's correct. I'm pretty sure that's correct. Okay, now we can get back to the code. Yes, so that was it. And we wanted to test. So here's my, we can go back here. So we go in steps. That was part 2. Then part 3 is A and B. Then we're going to check the velocity for the data dictionary. T, just temperature for the data dictionary. Absolute value is in the last column, but now I actually change. I shouldn't state that, so I can remove this. Mean velocity here is just we just take the mean of the absolute value, right? Then we have the mean kinetic energy, right, is 0.5. Just the mass of hydrogen and mean velocity squared, right? Then the theoretical mean kinetic energy is now 3 over 2, like we had. And we had, it was this guy here, right? That guy there. We can go back to the task so we can see. Yeah, 3 over 2 kT. So these should match. So the theoretical mean kinetic energy and this analytic, or you could say theoretical energy, it's 3 over 2 constant, and then of course Boltzmann constant and the temperature, and then the theoretical mean velocity, and it's like I said 8, Boltzmann constant, and temperature. Perfect. And then pi and mass of hydrogen. So I was completely right. And then we can see our data here, so we can test it. So let's run our data dictionary so we can see. So let's go back. Let's go to the assignment, of course, and then we can go. I just call it start for now. And there you can see the values are very good because the kinetic energy, you see 1.7, but it's 10 to the minus 19. And this guy also is very close to the same, right? The energies here are very close and they make sense, right? If you've done any energies, this is a minus 19 is a very typical number, okay? And then the mean velocity from data is this number here. And you see the theoretical mean velocity from data is this number here. So pretty much the same thing. So our data is perfect. Okay. Now the last step, I haven't finished that. It's this guy, not last step today. It's to simulate the particles. I haven't decided yet how. I think I started too heavy. It just states that we should just look at one particle, and we want to simulate that. And I tried to make some kind of complicated array for all the particles and the steps and the dimensions, and that, yeah, that just got out of hand. So I'll try again on Friday. Yeah. Okay, so I can just explain here. To test the pressure of the gas, first look at one particle with its given velocity and think how this particle will continue moving. How can you find a new position of the particle after a short time step? And that's just Euler method, of course. If I'm standing here and I have my position here and I want to know the next position, all I need to do is do the derivative, which is just the velocity. So if I also have the velocity that I will have at this position, I can move myself here with that small velocity for a small time step, right? And now I suddenly have a new position. If I always know the velocity, and we do because the velocity is just the same all the way, right? I can just calculate the new position all the time, right? I may have to change if I hit something, but that's just direction also, because we are assuming that all collisions, even with the wall, are elastic. So that is for the most part it. Yeah, so I haven't done this step here, but we are getting close. And just see what were I doing? Simulate particle for the dictionary. Yeah, and I just started with one. I couldn't get what I really wished for, which would have been fun. I would have. What did I think of first? Yeah, I would have, instead of having the particles as rows, I instead imagine having each particles as columns, but where every column themselves would also be a vector, right? And then each row would be the step, so I could just get the next position, next position, next position. But that didn't entirely work. That was so sad, because that would be so great if I could do that. But that's it for now. I'm going to continue with this assignment on Friday. I think I'll finish it then. So that's good for now, and I'll see you tomorrow.